11:05. Good morning, everyone. Welcome to ML Ops Production and Engineering New York 2021, hosted by ML Ops World. Our speaker here today is Jaya Kawale, and she's the Director of Machine Learning at Tubi. Her team is working on solving various ML problems for the product, ranging from recommendations, content understanding, and acquisition in ads ML. Prior to that, she worked at Netflix as a lead research scientist. She has also worked at Adobe Research and Yahoo Research in the past. She did her PhD in computer science from the University of Minnesota, working on graph-based approaches to understanding climate data. I would love to read that paper. That's very interesting to me. She has published several papers at various conferences like NeurIPS, KDB, IJCAI, SDM, and more. So welcome, Jaya, and take over. Oh, I should mention, I'm sorry, before you begin, I will be monitoring the chat. I encourage everyone, please put your questions in the chat. And at the end, there will be time for Jaya to answer your questions. Thanks. Thanks, Jaya.
Thank you. Thank you for the kind introduction, and really happy to be chatting about some of the things that we have been doing and some of the challenges that we face. So broadly, I will talk about machine learning for entertainment, some of the challenges and opportunities. Before I dive into the talk, here is the introduction. We'll talk about ML at Tubi, and then, of course, the challenges and solutions. So I'm not very sure if you've heard of Tubi, but Tubi is an advertiser-based video on demand service, which means that you can watch any content that is available on Tubi online for free. We have about 33 million monthly active users, and the number is only increasing. And we have a growing library of more than 30,000 titles. And very recently, we have also added sports along with live news content. So that is more different kind of content that you can watch on the service. So as you can imagine, there are three important pillars in any advertiser-based video on demand service. The very first important pillar is the content itself. The content represents the titles in the library, and it is one of the really key pillar for getting the second important pillar, which is the audience. Audience represents anyone who watches the service. And finally, because we are an advertising-based platform, we rely on ads for our revenue. The advertising is the third important pillar, which represents the ads shown to viewers on behalf of the advertisers. So as you can imagine, these three pillars are very interconnected. For example, more and better shows leads to more viewers. Bigger audience leads to more ads watched, and more revenue from ads leads to more better shows that we can buy. Also, more content attracts better brands to advertise on the service, and a more revenue means happier content providers. Also, bigger audience means happier content partners, as well as balanced and relevant ads. If we show you lesser number of ads or balanced number of ads, we will have happier viewers. So these three pillars are really interconnected to each other. And as you can imagine, machine learning is a critical component in making the three pillars function together. So one of the key areas of machine learning is personalization. Anything related to the homepage, anything that you see on the homepage is personalized by machine learning algorithms. We also have another nuance in the form of news and sport content. And as a result, these content need to be treated differently as compared to the video content that we have. And we need to take care of the news and sport recommendations in the form of different kind of algorithms. Then container or row ordering, what rows should we show to the viewers? How should we order the content within the viewers? How should we organize the results when viewers search for a title? what title should we show in autoplay, and how should we notify or send messages to viewers when new content becomes available. The second pillar that we talked about was content. And if you take a deeper look at the content in the service, and right now I'm just talking about the video content, not talking about the sports and live news content because they have different kind of metadata available. But typically let's say we have a typical movie like Hunger Games, which launched into the service 2 times at least that I know of. And for every content that launches, we have a lot of external information. For example, we have information in the form of plot synopsis, Wikipedia articles, then Rotten Tomatoes or IMDb ratings, cast information, reviews, and genre information that we can get from IMDb and other sources, and maybe our own source of determining the genre, and also the box office information. So this is a lot of information, and what we can do is using some of the first and third party data, we can try to understand the content itself. And a lot of this content is in the form of text, and some of the content is in the form of structured graph, for example, cast information and other things. So what we can do is create embeddings and models that help power several downstream applications. One of the key use case is cold starting. How do we cold start titles onto the service? Another use case is content value assessment. How should we determine what title should we bring in at Tubi? Once we understand the content and the audience better, we can make a good prediction about what titles would work well at Tubi versus what titles will not work. And similarly, there are a lot of other use cases: search, seeding audience growth, audience assessment, and other things that we can do once we get the content understanding piece right. Ads. So definitely there is a lot of things that can be done in the ad space with the help of machine learning. For example, finding the most relevant ad and so on. But I want to particularly focus on 2 computer vision based projects that have been going on at Tubi. One is to control the frequency of the ads itself. Remember, whenever we get ads on to show on the website, they can come from various different sources because the ads come in real time from various trade exchanges, and some of them could come from our direct partner sources and whatnot. So we do not exactly know the metadata associated with the ad, and so somehow we need to determine the brand of the ad so that we do not show you repeat ads of the same brand again and again. Another area where machine learning is heavily invested is trying to find out how to optimize the ad break itself. Where should we place the ad pod? How many pods should be there? How many ads should we show? What should be the duration, and so on. Um, so yeah, this in short is a high level overview of the machine learning things that we do at Tubi. And I want to focus today on some of the challenges that we face in real world pipelines. And I will also talk about some of the solutions that we have for the challenges. Uh, so I'm going to highlight these 4 challenges: balancing metrics, feedback loops, model interpretability, and algorithmic fairness and biases. But that being said, there are many, many more challenges that are there in a real world application. But for today, let's just focus one by one on these challenges. So the very first challenge that we face is of balancing the metrics itself. So typically you will see that when we train a machine learning model for recommendation or ranking, typical ranking metrics are in the form of NDCG, NMRR, precision at K, etc. And typical online metrics are in the form of streaming, retention, and so on. And as probably you all know, there is definitely a mismatch between the offline and online metrics. Um, and let's try to dive a little bit deeper and try to understand why is it the case. So the offline evaluation typically uses historical data. It is cheap, it is fast, it is risk-free. But one of the big problem of offline evaluation is that I'm sorry, my son just entered my room. Ugh. Um, but one of the key problems with offline evaluation is that uh, it's correlation based, meaning that the data that we gather are used to generate the metrics. And there is, we know counterfactuality of the rewards. So in short, we cannot capture with the offline data what would have happened if we would have shown something else and not this. And this is really critical because this leads to correlation based models only, and which is a huge limitation. On the other hand, the online evaluation is typically done with the help of randomized experiments, A/B test. We typically wait for a few days to compute the reward. It is a reliable process. However, it is expensive to carry out the A/B test. Um, so the offline-online mismatch is actually exacerbated by the dynamic environment in which typical machine learning algorithms operate. For example, the recommender dynamics can affect the performance in ways not captured by the offline metrics. So just to take a quick example, we could have impression caps, and this is a very it's very typical to have impression caps to not to show a title repeatedly to users. And as a result of this, this is impacting the performance of the recommender system itself. And these kind of things are not captured by the offline metrics. Another thing is that recommendations can influence the user preferences in ways not captured by the offline metrics. So many a times you will see that you watched a title because it was recommended to you, and you just feel that, oh, this is something interesting, maybe I can watch it. And this kind of dynamic is not captured by the offline metrics itself. Another important aspect is that the user dynamics and confounding factors can influence the watch behavior. However, this cannot be captured by offline metrics. For example, if you're watching a title because it was recommended to you by a friend of yours, this is not captured by our offline metrics. Um, so definitely there is a need to have a better offline evaluation. And I'm just going to highlight one such approach for unbiased offline evaluation. There is an entire area of research, but the first paper by Li Hong Li et al. Around 2010-2011 started the discussion around unbiased offline evaluation. So they mentioned this, the very first algorithm that they mention is what they call replay, in which you replay the data offline as if it were going through an online process. So there are several requirements for that algorithm. What you need to do is to generate uniform exploration data. By uniform exploration data, I mean that you need to randomly show titles to the users to get uniform data so that the data is not biased by any algorithm. And in that particular approach, what you would do is that you would choose a reward offline when you're evaluating a policy only when there is a match between the recommendations from the logging policy, which is your uniform exploration policy, and the policy that you want to evaluate. Um, So one of the advantage is that it's an unbiased estimator. The cons is that it has a huge variance. There is a huge amount of research done after this very first algorithm, and there are several variants which are based upon non-uniform exploration data and production data itself. What people generally try to do is try to do some correction to make sure that you are correcting for the title's propensity to be shown. For example, some titles are more likely to be shown, and as a result, they will more likely get more clicks. And so offline, you will need to correct for this before you can proceed with your evaluation. Next and related concept that I want to talk about is feedback loops. So what exactly are feedback loops? And feedback loops are so much present everywhere, not just in Tubi, but you will see that creeping up in other online systems as well. So what happens over here? So first of all, there are different algorithms on the Tubi homepage which are influencing one another. Typically, what we have is a different algorithm for continue watching, maybe a different algorithm for search, maybe a third different algorithm to show the most popular titles and whatnot. So there are different algorithms to organize the different containers on the homepage, and maybe there are different algorithms which take care of the ranking of the containers and whatnot. So there is definitely an influence of one algorithm on the other. The underlying data that we get from from the feedback influences the algorithms itself, and the recommendations influence the watch behavior. The watch behavior influences the data in turn. So there is a loop. You gather the data from whatever you have shown to the users, and the data that has been gathered is used to train an algorithm that will be shown to the users again. So this creates a cycle or a feedback loop. Uh, why does this feedback loop happen? So typically you will see that in offline training, we rely upon clicks, watches, plays, and we use implicit feedback. And implicit feedback itself has inherent biases, position of the recommendations, etc., influence the data collection. So let's look at some of the techniques to break the feedback loops. And one of the popularly used techniques is exploration and bandits. So what exactly is a bandit? At the heart of a bandit algorithm is this trade-off between exploration and exploitation, which means that the bandit algorithm will decide whether we should explore unknown choices to gather information or exploit known information to show the best or the most optimal titles to the users. So exploration inherently helps break the feedback loop because you are showing some unknown choices to gather more information about them. However, one of the caveats over here is that there is inherent bias typically in contextual bandit algorithms. When you do an adaptive assignments of context to arms in the contextual bandits, arms are basically the titles that you want to show in the service. There is a bias in this assignment itself. However, I would say that the exploration and bandits is a very simple and a good approach to break the feedback loops. Uh, Another approach is based upon weightings or matching of models, and this idea comes from the literature of causal inference. So in causal inference, basically what you want to do is, let's say when you assign a population to treatment and control group, the typical assignment is biased because let's say if you assign a patient to give certain medicine, you are doing it based upon different factors, and the assignment is typically not random. Um, so what you want to do is you want to estimate the treatment effect under unconfoundedness. So remove all the confounding factors and try to estimate what is the actual treatment effect. Whenever you show an ad to the users, did they click on the ad because they would have otherwise clicked anyways, or whether they clicked on the ad because they liked the ad. So the idea from causal inference is that the assignment to treatment is conditional on the feature space X. And what you can do is reweight the control group to look like the treatment group in terms of the distribution of X. Propensity score kind of models are typically used. So what they do is they assign, so the idea behind the propensity score model is to compute a probability to be assigned in a treatment given a set of observed covariates. Now, borrowing this idea, there is a lot of literature in treating recommendations as a treatment. And what they typically do is train a debiasing model in which you reweight the data itself using some kind of a propensity score kind of a model, and use this debiased model finally to show your recommendations. Another parallel line of work is counterfactual inference framework. Not diving too deep into it, but the idea over here was popularized by Swaminathan and Jacquins, and there are lots of papers in this direction. So the idea is that it's not sufficient to have an unbiased estimator of the off-policy performance, but you have to reason about the variances of these estimators across the hypothesis space and choose the hypothesis with the best possible guarantee. Let's move on to the third challenge, which is on model interpretability. Especially in the deep learning era, you will see all kinds of various complicated models that are really good at predictions. But when it comes to explainability, nobody knows why it is working. So it is very important to have model interpretability. And I know that there is a talk today going entirely into the model interpretability. But just to give a very brief overview, the interpretability is important to understand the bias, is important for debugging, is important for transferring the learning, and is important just for increasing the confidence in the machine learning model. So just highlighting a few quick ways for model interpretability. Partial dependence plots. Basically, you try to study the marginal effect of one or two features on the prediction. And some of the recent approaches rely on one of the two, either a global surrogate or a local surrogate. So the global surrogate approach, basically, what it does is an interpretable model is trained to approximate the prediction of the black box model. And then you use or you study the interpretable model to understand the predictions better. On the other hand is a local surrogate model, which is the local and one of the famous models in this family of models is the line model, local interpretable model agnostic explanations. And the idea behind this kind of models is that you do not try to explain the whole model, but instead trains interpretable models to approximate the individual predictions. And there is a whole line of research around this, and model interpretability is extremely important, and it is very important to look at like one of the choices to have better control over the predictions. Finally, I want to touch upon the topic of algorithmic fairness and biases. As you can see, like in typical ranking systems, we have a ranking function. The idea of a ranking function is to rank the items for a given context. And typically, we use some kind of learning to rank algorithms to rank the titles given the context. And for Tubi and other such similar websites, slate recommendations are important because you're basically showing a slate of titles and not just one single recommendation. So the question over here is, are traditional methods fair? And so one key thing to understand about fairness is that many aspects of discrimination relate to correlation versus causation. So gender and race may be correlated with factors that shift the distribution. And the reasons for biases that arise in the machine learning models could be different. For example, just because the examples are skewed, just because you don't find too many examples representing a particular gender or race, because of that you have skewed examples, you can have some kind of a bias. Tainted examples is another such thing. Limited features, you may not have good enough features to represent the minority class. That could be one thing. Sample size disparity, sometimes maybe you're just picking a very, very small sample size to make an inference, and that can cause biases as well. So typically for handling fairness in machine learning, there are three broad techniques which are used. In pre-processing kind of techniques, what is done is that distributions of sensitive or predictive variables are biased, and what you try to do is train a model on repaired data. So basically, you assume that the training data itself is biased because maybe it doesn't have enough representation from the minority class, or it doesn't have enough features. So what you want to do is create some kind of a repaired data and use or train a model on this repaired data set. In processing kind of approaches are basically what they try to do is incorporate fairness metrics itself into the model optimization process. So they say that the modeling techniques itself are biased because of dominant features or distributional effects, and you can maybe have a different optimization technique which takes into account that and comes up with a fair recommendation process. And finally, post-processing kind of techniques apply transformations to improve the prediction fairness. And these can operate on black box ML models. And basically, they don't try to interfere with anything that the model does. But at the end of the predictions, you just try to do some kind of post-processing to make sure that the recommendations are fair and are not biased. So I mentioned some of the typical challenges that we face and some of the solutions for these challenges. Here are some of the very good references that I found helpful. And I think the big opportunity over here is that together as a machine learning community, we need to solve some of these challenges. And these challenges are really hard challenges as well, to have a better machine learning system overall. That's all for today. Thank you.
Excellent. Thank you so much. That's really interesting. As a culture, how do you bring in all the new research into operations? What's the process?
Pardon? Sorry, could you please repeat the question?
As a culture at Tubi, you've got all this advancement in the field, all this research going on. Do you have a separate research team? Is there a pipeline to feed into the ops guys? And what's your experimentation process?
Yeah, we are a fairly small company, so we don't have a different research team, but the machine learning team itself consists of like maybe 20 plus people right now, focuses on these challenges. So the first thing that we did was we just built a very basic pipeline in the beginning, and now I think we have the luxury to look at some of these problems, more challenging problems that we need to solve. And I would say that together as a team, we are trying to solve some of these problems, and some of the things that I have mentioned are already work in progress at Tubi, like exploration and bandits. These are some of the things that we are already working on.
So have you ever put anything into production and thought, uh-oh, we have to yank this. It's not quite ready for prime time.
So the things that I have mentioned are so subtle, like feedback loops and everything are so subtle that maybe you will not see drastic change within a day, but it happens over a period of time. So for example, the feedback loops. So what you would see is that the recommendations will typically, because of the feedback loops, will start focusing on a very narrow set of the library, because there is a huge feedback loop. You show the titles, and the most popular titles probably get all the love from the audiences, and then you use that to train your model again, and so on. So over a period of time, we did observe, it didn't happen overnight, but over a period of time, we did observe that, this is what is happening. Maybe we are focusing on a very small portion of the catalog, and maybe we are missing out on these hidden gems that can also benefit from some love from the audiences.
So we do have one question here I saw from Phil Godson. And you talked about how you incorporate, it's about advertising, and you talked about the involvement of the audience data, but he wants to know about the content, the contextual, using machine learning to look at the context of the content with respect to advertising. I don't think you touched on that.
Yeah. So unfortunately, that's not an area that we have done deeply at Tubi, at least as of now. I know that it's like the entire machine learning community in the ads world is dealing with those kind of problems. So far, since we are a very small company and we have literally just gotten started in the ad space, I just highlighted the two problems that we have made huge inroads on, but definitely there is relevance, ad relevance, etc. is a huge area in itself.
Thank you, audience, for your questions. We have another one coming in here from Jesse Wildman. Many financial service firms are not deploying deep learning models due to the regulatory environment. Being in a non-regulated space, how are you thinking about deploying deep learning? The freedom of non-regulatory spaces.
Yeah. Definitely. So deep learning is, as I think everybody has seen in the past few years, the models are really, really powerful. So we want to, we want to have the latest state-of-the-art models for showing the recommendations and whatnot. So definitely we use deep learning models. And some of the things that I mentioned for content understanding, especially when you have a huge amount of text data, I think deep learning for NLP is the state of the art. So we are forced to use deep learning models for some of the problems.
Yeah, it seems like instead of forced, a bit of a luxury.
Yeah, exactly.
You have the power to use the big tools.
Yeah.
I don't see any more questions. You gave excellent references, so thank you. Gives us lots to think about and lots to go on to learn about. Thank you for your time and your sharing your experience and your excellent presentation, Jaya.
Thank you. Thank you for inviting. Thank you.